Hello everyone, welcome to our discussion of section 9.4 where we will be talking about calculating area and length of an arc when we have polar coordinates. Now the first thing you see on the screen is the basis of the formula that we have for the calculating the area using an integral or calculus methods. We learned about this formula way back in basic geometry or elementary geometry. It basically says that the area of a circular sector or the area of a sector of a circle is equal to half the length of the radius squared times the angle that the arc subtends. So this is just coming to us from elementary geometry. Now, the formula for the area of region, region whose boundary is given by a polar equation, is based on that. So here we have, suppose we are calculating the area of this region, and which is bounded on this side by some equation that is being given to us using polar coordinates. And then notice that the boundaries of the integral are from theta equals a, measured from the positive side of the x-axis to this boundary of the region, and then theta equals b, which is the upper limit of the integral, which is equal to this angle from the positive side of the x-axis to the other boundary of the region. And of course, f of theta is the equation for r in terms of theta, so we square that and then times 1/2. So I'm sure you can see the similarities between this and that formula from way back basic geometry. Okay, so we can replace that f of theta with just r. So these two are forms that you might see in the book or someplace else. Okay, having said that, let us start with a simple example. Here we are asked to find the area of the region that is bounded by the given curve and lies in the specified sector being 0 to pi over 6. Okay, so we're going to apply that formula. In fact, if you remember the formula, or if you want to back up on the video and write down the formula, and pause the video then and write the solution for this on your own. So that would be a good idea if you want to start right off the bat with that. I'm sure you can do it, but it's always better to get a practical sense of these calculations rather than just watching them all the way through. All right, so we have the formula that says from 0 to pi over 6, integral from 0 to pi over 6, 1/2 r squared d theta, right? We have that. So that will give us, we're going to replace r with cosine theta, and then we're going to square that. D theta, and of course we can put the 1/2 in front of the integral, so let me do that. And then we can distribute that power into the cosine function, d theta. Now we've used a formula to simplify this integrand several times, but let me refer to it again. So recall that cosine squared theta is equal to 1 plus cosine 2 theta over 2. This is a very useful formula, and most of the times we have to simplify in this direction. In other words, go from the trigonometric function squared to that one, Once in a while, it's easier if we go the other way, especially if you have a square root. If you have a square root in the integrand, then if you go back, if you can apply this somehow and go back this way, it's really useful because the square root and this power cancel each other and you end up with cosine theta. So just keep this in mind. Whenever you have square root, you might be able to use this formula if other formulas are not available. But this is a very useful formula for us. And from that, we can write 1/2 of the integral from 0 to pi over 6. And instead of cosine squared theta, I'm going to put in 1 plus cosine 2 theta over 2, right? This replaces that in the integral, like that. And then, of course, this whole thing is being multiplied by, or divided by 2, so we can pull out this as a factor and multiply it by this 1/2. So we have 1 over 4 times the integral from 0 to pi over 6 of 1 plus cosine 2 theta d theta, right? That's pretty easy now to integrate. So let's jump right to that. And then we have 1 over 4 times integral of 1 is just theta. Integral of cosine 2 theta is 1/2 times sine 2 theta, right? So plus 1/2 sine 2 theta. Of course, this is going from 0 to pi over 6. Okay, so let us evaluate this inside of this bracket at theta equals pi over 6 and then theta equals to 0. Notice that for 0, both terms drop out, right? Sine of 0 is just 0, theta 0 is 0. So only for pi over 6, we're going to have some meaningful or some non-zero value for this term, for these two terms. So we have the area equals that, pi over 6 plus 1/2 sine 2 pi over 6, right? This 2 times that. And if I put both of these inside the parentheses, then we can say minus, for substituting 0, we just get 0, and then we can close the bracket that way. Okay, so what do we get here? We get 1 over 4 times pi over 6 plus 1/2. This is, when you simplify, 2 pi over 6 simplifies to pi over 3. Sine of pi over 3 from trigonometry, we know it is equal to square root of 3 over 2. Okay, and of course, that's just 0. So then the area, if we multiply everything or distribute everything through, we get pi over 24 and plus, so 2 times 4 and then 4 times 4 is 16. So we get square root of 3 over 16. And of course, we want to leave the answer in exact form. We do not want to calculate the decimal version of this. Okay. If you pause the video and did this on your own, I hope our answers agree. And if it does, that's wonderful, because that means that first example, you got perfect score. So here's another example. The same idea. We want to calculate the area of the region that is bounded by the given curve and lies in the specific sector. So this R, of course, it's always going to be greater than or equal to 0 because of the R squared, and theta we want it to range from 0 to pi over 2. Okay, I strongly recommend that you pause the video and then we'll compare solutions that way. Okay, so area given this polar equation is equal to limits of integration 0 to pi over 2, and then 1/2 r squared d theta, right? That's the fundamental formula. Notice that in this case, r squared, we don't have to square this side because it's already, that right-hand side is equal to r squared, so we can just plug in this into the integrand as it is. So we have then a is equal to, and right off the bat, I'm going to put the 1/2 in front, so 1/2 times integral from 0 to pi over 2. Instead of r squared, let's plug in the whole thing, right? That's equal to r squared d theta. Of course, that 9 in front can also be factored out and placed in front. So when we do that, we get 9 over 2. And then we get integral from 0 to pi over 2 of just sine 2 theta d theta, right? Look at that. That's a pretty easy integrand for us to integrate. So we have, let me integrate immediately. So we have 9 over 2 times integral of this. This must have come from a cosine. Of course, in a derivative of cosine would be minus. So in our integral, we must have minus. And then to get rid of this 2, when we take the derivative in the integral, we need a 1/2 cosine 2 theta going from 0 to pi over 2. If you ever have doubt, of course, I know you know this, but if you ever have doubt about this, just take the derivative of this. Do you get that? And if you do, then you know that you've done the steps correctly. So you move to the next step. All right, this is the fun part. We just plug in pi over 2 for theta and then 0. We have to be careful here because for cosine of 0, we get a value, right? Cosine of 0 is just 1. 1 times minus 1/2 is minus 1/2. And then, of course, there's a minus in front of that. So we have to remember all of that. If it's a sine, it just drops out, like the previous example. If sine of 0 is just 0, but cosine, we have to be careful because we do get a non-zero value. So we have then 9. By the way, we can factor this out too, so why not do that? So minus 9 over 4, right? And then the rest cosine of 2 times theta, so 2 pi over 2, and then minus cosine of, because we've already factored out minus 1/2 into this, so we don't have to worry about it. So cosine of 2 times 0, right? This 0, close bracket. So we have area equals minus 9 over 4 times these two, this and this cancel, we get cosine of pi. Cosine of pi is of course -1, but let me also go through that simplification step here. And then minus cosine of 0. So we have minus 9 over 4. This is just minus 1. Minus cosine of 0 is 1, minus 1. And then close that. So we have minus 2 times minus 9 over 4. We have positive 18 over 4. Or simplify this, we get 9, positive 9 over 2. Okay, I hope this is the same answer that you got. Here we want to find the area of the shaded region. So sometimes the graph has been provided to us, like in this case. Sometimes it's not provided and we have to draw it. And these are, I mean, this is not too bad to draw by hand, but most of these graphs are difficult to draw by hand, so you are welcome to use technology. Specifically, I recommend Desmos.com calculator. That's an outstanding site that you can immediately, in a matter of seconds, you can see how complicated equations look in graph form. So if the graphs are not given, feel free to use that tool to get an immediate visual idea about the graph of the equation. Okay, so we have here, so this is from 0 to 2 pi gives us the whole region, right? So from 0 to pi will give us the region that we're looking for. So if I say 0 here, well, since this is a polar, for the pole, we have the coordinates 0, comma, theta. And of course, theta can be any value, and it's equivalent, right? We learned that for any point in polar form, there are many equivalent polar coordinates. So we can have 0, comma, 0 for that. And in fact, we're going to take that as that. And here we get to pi. So we have pi. I'm just going to put pi here like that. Okay, so and then we have, having said that, I just want to make note of that we are using half of that. So let me actually write that down. So the full cardioid, which is that shape, is traced over the interval 0 to 2 pi. Right, but we want half of that, so we're going to go from 0 to pi. Is when theta is ranging from 0 to pi. Okay. So we have the area going from 0 to pi, 1/2 r squared d theta, right? And then we have, I'm going to put the 1/2 in front, so we have 1/2 integral from 0 to pi, r squared, that is our r, 1 plus cosine of theta squared, d theta, right? So we can expand this to get a simpler expression. One half, of course, it's going to be here. Let me just put it here like that. 1/2 times 0 to pi. Expanding that, we get 1 plus 2 cosine of theta plus cosine squared theta d theta. I know you remember this, but I'll write it for the sake of your notes anyway, so that you have this on the paper. Recall that the cosine squared theta is 1 plus cosine 2 theta over 2. And if this is sine squared theta, we're just going to have 1 minus cosine 2 theta, right, for sine squared theta. So we're going to substitute, because these two terms are easy to integrate. It's the problem with this one, where we have to utilize this formula so we can make it easy to integrate. So then we have the area is equal to 1/2 from 0 to pi of, let's see, so we have 1 plus 2 cosine theta plus 1 plus cosine 2 theta divided by 2 d theta. Okay. All right. So now it's easier if we separate the 1/2 plus the 1/2 times cosine 2 theta. Let's separate these two terms. So we have area equals 1/2 times 0 to pi of 1 plus 2 cosine theta, and then plus 1 over 2, right? This is the common denominator to these two terms. So 1 over 2 plus 1/2 times cosine 2 theta d theta. Okay, let's move this up. So now, let's see, we could immediately integrate, but we have to combine these two constants. 1 and 1/2 add up to 3/2, right? So the area is 1 over 2 from 0 to pi of 3 over 2 plus 2 cosine theta and plus 1/2 cosine 2 theta d theta. Okay. All right, now we can integrate this. So we have area equals 1/2. This is just going to be 3/2 times theta. This is going to be 2 times sine theta. And this is going to be 1/2 times 2 times sine, or 1/2 times 1/2 again times sine 2 theta, right? So we have, overall we're going to have plus 1 over 4 sine 2 theta, and from 0 to pi. Okay. So if you take the derivative of this, do you get that? Yes. Right? 1 over 4 times cosine 2 theta times 2 by the chain rule, we get 1/2 cosine 2 theta. So everything is good there. And now let's replace theta with these parameters. So we have area equals 1/2 times, what do we get? We get 3/2 times pi plus 2 times sine pi. That's going to be 0, right? Plus 1 over 4 times sine. This is 2 theta, so it'll be 2 pi. And of course, because these are both sines and this is theta, so if you plug in 0 for the theta here, you get just 0 all the way. So we're just going to say, I'm just going to put this group in parentheses and then say minus 0. And then we'll close the bracket that way. Okay. So the area is equal to these two terms. 2 sine pi will be 0. 1 over 4 times sine 2 pi, also 0. So we're left with 3/2 times pi, right? 1/2 times 3 pi over 2. Therefore, the area is 3 pi over 4. Okay, I hope this matches what you got in your own calculations. Let's go to the next example. So here's another one. Again, these equations are getting more and more complicated. So I did draw, and here is what I'm recommending. Use either a calculator or a computer to graph this curve, which is that one. And for example, this, I'm recommending that website again. Okay. So with this graph of our equation, and they want, in this case, they're not shading, they didn't say, like the previous example, to find the area of the shaded region. This was the case we had before, right? But in this case, they just say, find the area enclosed by this curve. So it's the whole thing that we're calculating. And when you do this on this, when you graph this on desmos.com/calculator, it gives you all these numbers too. It does a really nice job of this. And the graph is much more symmetric than what I've done on paper. Okay, so let us then apply the formula. So this would be 0 to 2 pi, right? To trace the entire curve would be from 0 to 2 pi. So we have A would be from 0 to 2 pi, 1/2 r squared d theta, right? This is our formula, and we know this is going from 0 to 2 pi, the whole thing. All right, so let's substitute for r squared. This is, of course, a square root. When we square it, this will go away, and we're just going to have 1 plus cosine squared 5 theta. But let me just simplify it to that. So 0 to 2 pi, 1/2 times square root of 1 plus d theta. Okay. All right, so in the next step, we're going to simplify that to just 1 over 2 integral from 0 to 2 pi of 1 plus cosine squared 5 theta d theta. Okay, and then recall that useful formula, right? Cosine squared theta is equal to 1 plus cosine of 2 theta divided by 2. Of course, in our case, the theta in this formula is 5 theta. So when you plug it in here, you get 2 times 5 theta, or 10 theta. Okay? So we have to adjust for this parameter that we have. Okay, so we have A equals 1/2 integral from 0 to 2 pi, and we have 1 plus cosine of 10 theta divided by 2 d theta. So let us, again, like the previous example, let us separate the constant from the trigonometric function here. So we have A equals 1/2 times 0 to 2 pi, and then we have 1 plus 1 over 2. And I know in basic algebra we always talk about how to take the common denominator and combine terms, but here we're going the opposite. So we have 1/2 cosine of 10 theta d theta. So of course these two we can combine, right? 1 plus 1/2 is 3/2. Let's do that. Plus what we have left. d theta. And now we can integrate easily. So we have a equals 1/2 times 3/2 theta plus it'll be 1/10 times 1/2, so that'll be 1/20, and then sine 10 theta, let's see, so we have, what do we have? We have sine 10 theta, correct. So we have plus 1/20 sine of 10 theta, and then we have this from 0 to 2 pi. All right. Okay, so I think I have enough room to finish this on paper. That's what I predicted based on my notes. So let us substitute the inside. So we have, for 2 pi, we have 3/2 times 2 pi plus 1/20 times sine 10 times 2 pi. It's going to be 20 pi, right? And then we can close this, and then we can say minus, because all we have is just theta times a constant and a sine function. When you substitute for theta with 0, both of these terms drop out, right? If we have a cosine, we have to be careful because we're going to get a non-zero constant, but we have a sine here. So minus 0 and then that. Okay, and let me just move up here a little bit. I need just a little bit space here. So we have area equals 1/2 times 2 pi times this. 2's cancel out. We end up with 3 pi. And then this is just 0. 20 pi is just going around and around the figure, or tracing that path 10 times, right? So like that. So that just goes back to the 0. Theta equals 0, which sine of 0 is equal to 0. Okay, and then we have, so in the end, we end up with area equals 3 pi over 2. Again, I hope this matches what you worked out on your own before you watch this video. Okay. Let's do another example here. Here we have sketched the curve. So this curve wasn't there. Sketch the curve using technology. Good advice, this is. And find the area of the region enclosed by one loop of the curve. Right? So we did that. You can easily do this at desmos.com/calculator. Do it, as a matter of fact. Make sure that your graph matches this. And they're saying find the region enclosed by one of the loops. Okay. So we need to know then, looking at this figure, we need to know obviously it starts from 0, but from where to where we're going to trace this loop only. Okay, so so we have, so the shaded region here, I think on Desmos, it allows you to, once you enter a polar equation like this, it allows you to set the interval for theta. So you can try out different theta values. Use simple ones like pi, pi over 2, 3 pi over 2, things like that, and see when you're going to get that loop only, not the rest of it. So if you do that, so you'll see that the shaded region since this is r squared, so the equivalent would be just r equals sine of 2 theta. And then this will happen for theta ranging from or going from 0 to pi over 2. So experiment with this with different theta values on Desmos.com. Okay, so from this curve, from here to 0 to pi over 2, it should give you just that piece, or trace this. This is the same thing as that. Okay, so then, and we can add by the same token, let me just add the unshaded region, the unshaded piece, this one, and is traced out by r equals minus that, right? Because if we take the square root of both sides, we get plus or minus. So we're interested only in the positive. Minus sine 2 theta. Okay, so let's just apply the formula we have. Area is equal to 0 to pi over 2, and then 1/2 times r squared d theta. So these limits of integration are not given to us. So you're gonna have to use technology, either a calculator or a computer or a website, to come up with that. Okay, but you do know what you're looking for. Just try different parameters for theta until you get just that piece. That's all. And then we have so this is then area equals, I might as well just put the 1/2 in front, from 0 to pi over 2, and then so instead of r squared, let's plug in sine 2 theta, and in case you're wondering, I didn't need the parentheses, so I could have just said sine 2 theta. Okay, so we can integrate this right away. We get 1 over 2 times antiderivative of this, it would be 1 over 2 minus 1 over 2 cosine 2 theta. And then we have going from 0 to pi over 2. Oops, sorry, I apologize. I was off the screen there for a little bit. Okay, so now then let's multiply this by this. So we have minus 1 over 4 times cosine of 2 times pi over 2 minus, here we have to be careful because we have a cosine at 0, right? So cosine of 2 times 0, and that's going to be a non-zero value there. So let's be careful there. Minus 1 over 4, and 2 and 2 cancel out. Cosine of pi would be minus 1, right? So these two cancel out. And then minus cosine of 0 is also 1. So we have minus 2 times minus 1 over 4. We have positive 2 over 4, or the area being equals 1/2. Okay. So I'm sure you notice without this graph, we wouldn't know how to, or without technology, it would take many, many hours to figure out which part from theta angle, where to where, we would get just that piece. Okay, so please make yourself familiar with the technology so these kind of problems become pretty easy to handle. Here's another similar example. We want just the area of that region enclosed by that loop. Okay. So first thing, the entire domain, because this curve goes beyond just the loop, right? So we're interested in knowing for which theta values we're going to get just the loop. We don't care about the rest of this. Just the loop is what the area enclosed by the loop is what we're interested in. So with technology then, you can see that this is happening between 0 and pi, and let me make a note of that. Using technology, well, no, sorry. So I'll take that back. So the entire curve, this is for the entire curve, then including these whiskers that come off this way and that way. So the entire curve has a domain from 0 to pi, not just that piece. I apologize. So the entire curve has the domain from 0 to pi, where of course because of that term, not that, because of this term, because this is the reciprocal of the cosine, 1 over cosine, we can't have theta being equal to pi over 2. So this is the domain of that, and the only exception is where theta is not equal to pi over 2. Okay, because of that term. It's going to be undefined, since this is 1 over cosine theta. And cosine theta would be 0 at pi over 2, so we can't have that in this interval. Okay. And then, so the curve really is going through the origin or the pole twice. So let's see if we're going to have to find out after tracing what angle. So it starts from 0 and then it goes through the pole after tracing some theta, right? And we need to find out what that theta is. Okay, so actually, so this point is 1, 0, right there. Okay, so when theta is equal to 0, it's here. not there. It's there, and then so we need to find out at which point this curve, after tracing what angle this curve goes through the origin. So it's not going to be at theta equals 0, because at theta equals 0, it's at this point. Okay. All right, so let's find that out. We know that at pole, r is equal to 0, right? Let me, as a reminder, so the coordinates of the pole are 0, comma theta. Theta can be any angle as long as r is 0. So this is r comma theta. R is equal to 0 at the pole. Okay, so let me write this down. When the curve passes through the pole, which is 0 comma theta, we will need to have or satisfy this equation, r equals 0, right? R equals 0. So that means we're going to put r equals 0 and solve this equation for theta. Okay, let's do that. And then we have, let me convert to cosine version. So 2 cosine theta minus 1 over cosine of theta equals 0. And then we can write 2 cosine of theta equals 1 over cosine of theta. And then we have, so this would be cosine squared theta equals 1/2. So given that, then we have, so then cosine of theta is equal to plus or minus square root of 2 over 2, right? Square root of 2 over 2 after rationalizing the denominator, because it's going to be 1 over square root of 2. After we rationalize that, we get the square root of 2 over 2, plus or minus. Okay, so this, if this is true, to be true, then theta has to be either pi over 4 in the first quadrant or in the second quadrant where we have the 3 pi over 4. Okay, so let me write that here. So theta has to be either equal to pi over 4 or 3 pi over 4. And so for that interval that we have, 0 to pi, and like that. Okay. So we can really take, so we can just use pi over 4. Right? That's going to take us from here to here. And then because by symmetry, this region would have to be equal to that piece above the x-axis. The pieces above and below the x-axis would have to be equal. So we can just say 2 times integral from 0 to pi. No, it's 0 to pi over 4, sorry. 0 to pi over 4. So let me, as a matter of fact, let me draw this as a dashed line. So pi over 4 dissects the quadrant, right? even if I cannot draw it symmetrically or accurately, it should dissect the quadrant like that. So this is our theta equals pi over 4. Pi over 4, right? So we can integrate from 0 to pi over 4, which will give us this piece, and then we can multiply the integral by 2 to get this piece, since these two pieces are equal, the area pieces. Okay, let's do that. I'm just going to add a note, however, here, that by symmetry, so we can double the integral from 0 to pi over 4. Okay, so this is our doubling the integral from 0 to pi over 4, 1/2 r squared d theta, right? So then we have, so r is this whole thing. I'm going to plug that in. So even though this problem didn't ask us to graph it, without the graph really, or without the use of technology, we wouldn't have any way of establishing these limits of the integration. And so we have, so 2 times 0 to pi over 4, and 1/2 times all of that, 2 cosine theta minus secant theta squared d theta. Okay, and okay, let me, guess I need a new page here. Okay, so we have A equals, and then so this one, this 2 times 1/2, they cancel each other out. So we get 0 to pi over 4, and then all we have is take this binomial and square it, and we will get 4 cosine squared theta, and then minus 4 cosine theta times secant theta plus secant squared theta d theta. Now we know that this piece is just 1 over cosine of theta, right? So cosine theta times 1 over cosine theta, they cancel each other out. This and this cancel each other out. We end up with just minus 4. Okay, this times that, we end up with just minus 4 from this middle term. Okay, so let us, we don't need that. So then the problem then is for this one, not even that one. We do have integral of that is tangent of theta. Integral of secant squared theta is tangent theta. So that's an easy one to integrate. This one is just minus 4. So this is our problem, this one. But we have that useful formula, right? So recall, we have to recall two of these. Recall that cosine of 2 theta is equal to 1 plus cosine 2 theta divided by 2, and also integral of secant squared theta d theta is equal to tangent theta. And I'm not adding the c plus c here, even though this is an indefinite integral, because pretty soon we're going to have the limits of integration involved there. But so this integral is equal to that. So let's substitute for this piece only, is the one that we have to simplify a little bit. Okay, so we have the area equals 0 to pi over 4, and then we have 4 times, right? 4 times, so 4 times 1/2 times 1 plus cosine of 2 theta, like that. And then minus 4, of course, which is that result, plus secant squared theta d theta. Okay. So distributing this 4 into this, what do we get? We get integral from 0 to pi over 4. And so this would be just 4 times 1/2 times that. It will be 2. And 4 times 1/2 is 2 times cosine 2 theta. So plus 2 times cosine 2 theta. And then minus 4, of course. And then plus secant squared theta d theta. Right? So we have minus 4 and positive 2. They combine to give us minus 2. Right? So we have A area equals integral from 0 to pi over 4 of minus 2 plus 2 times cosine of 2 theta plus secant squared theta d theta. Okay. And then, so we can integrate this. We know that's the rest of it is just easy to integrate. So we have this one would be minus 2 theta. This one would be plus 2 times 1 over 2 times sine of 2 theta plus, of course, tangent of theta, which we noted earlier, right there. Okay. So these are also, these integrals are also in the back of your book too. All right. So all of that going from 0 to pi over 4. All right. So we have, let's substitute, we have area equals minus 2 times pi over 4 plus 2 times 1/2 is just 1 times sine 2 pi over 4. Of course, that's going to reduce to pi over 2 eventually, plus tangent of pi over 4. So tangent at 0 is 0. Sine of 0 is 0. Theta at 0. So all these terms drop out for this parameter of for this limit of an integration. So maybe I should have put minus 0, but it's going to drop out anyway. Okay. So then area would be equal to minus pi over 2. Right? Minus pi over 2. Sine of pi over 2, it's 1. positive 1, and tangent of pi over 4, or 45 degrees, is also 1. Right? So we can just say the area is equal to minus pi over 2 plus 2. Okay, and we'll leave it like that. If you prefer, you can write 2 minus pi over 2. All right. So next, we want to talk about the area of a region bounded by two polar curves. So everything we've done so far, it was just one curve that was given to us in polar as a polar equation. But now, what if we have two curves given to us in polar form, and we want to calculate the area enclosed by them? So let's call, for the sake of our formula, let's call this top or higher curve f of theta, and then the other one, the lower curve, g of theta. And let's say we want to integrate from theta equals a to theta equals b. Okay, so here's just a description. You can read what are the conditions for all these things. For example, notice here that we say that f of theta, well, let me bring this down a little bit, f of theta is assumed to be the higher curve, so greater than or equal to g of theta, and both of them are greater than or equal to 0. So both are assumed to be positive values that trace each curve. Those are just positive values. Okay? And this is just for limits of integration. And so then the area of that region R is found by subtracting the area inside g of theta from the area inside R equals f of theta. Basically, they're saying, so the shaded region is the area that is the result of finding all this area, which would be f of theta. Using the method that we've discussed so far, we can calculate that entire area. And then applying that same formula that we've been using so far in this section to this one, to g of theta, we'll get this cone, the area of this cone. So if we have those, and all we have to do is subtract the area of this cone from the larger cone, and we get the area of the shaded region. Okay, so that's the idea behind this formula. And you can see this is just r squared, right? So this is r squared for the higher curve minus the lower curve squared. And then 1/2 is, of course, here too. All right. So on the next page, for the sake of your notes, I've captured some things that you can read and make yourselves familiar with. It's just saying that to find the area of the region enclosed by two polar curves, we need to find all the points where the two curves intersect. This is the heart of the matter. We need to do that. We need to find all the points where the two curves intersect, because these will be used to set the limits of integration. Okay? This means we have to find all the values of theta between 0 and 2 pi that satisfy both equations. So we simply set both equations equal to each other and solve for theta. That's what we do. Okay? Here's the difficulty. So that's the easy part. But however, so this is pretty important. This is, let me highlight it a little more here. This is worth rereading Make sure that you reread this if you have to. So, however, if the pole or the origin with coordinates 0, theta is one of the intersection points, it would be difficult to find the value of theta for which the pole will be on either curve. Okay? Simply because each curve will attain its origin at different time. Okay? So we got to be careful there, because the theta that achieves, that the theta value that takes one curve through the origin, it's not necessarily going to be the same theta that takes the other curve through the origin. That's what this is saying. And we need to find out what that theta is for each curve. So for this reason, to find all points of intersection of two polar curves, it is recommended that you first draw the graphs of the curves using calculator or computer technology. Okay, so this is just a note before we see some examples in this area. So here's one. The graph here was not given. I got this graph using the desmos.com/calculator. So r equals 1 is simply a circle of radius 1. That's all. So that's the blue circle, or it's the circle with the blue boundary that you see. The other curve, or the cardioid, is this one. Okay, so after you trace them, you trace both polar equations on the graph, it'll show you where they intersect. Okay, so it's integrating, they intersect at these 2 points. Notice that this point, you can call it either 1, 0 or 1, 2 pi. Okay, so we will need to, and the limits of our integration will have to go from, because the shaded region is from here to here, it will have to go from not pi to 0 or 0 to pi, but pi to 2 pi. Okay, so 0 to 2 pi would be up there. That's not what we want. Okay, so they're saying find the area of the region that lies inside the first curve. That's the first curve. And outside the second curve, which is r equals 1. Outside of this curve, inside of this curve. So that's that. Okay. Feel free to do this, to draw both of these curves on desmos.com/calculator. All right, so now that we have after we use technology and we have this graph, we know what our limits of integration ought to be. Okay, and then we can start integrating. But let me make a note of that the two curves here intersect intersect when this equals that, right? So let's just go through this, because we're going to have to do this again and again for the upcoming examples. So 1 minus sine of theta equals 1. And then let's solve this. We get, what do we get? We get sine theta, and 1 minus 1, it's going to be 0. So when will we have the sine of an angle equal to 0? That's when theta equals 0, or theta equals 2 pi, and theta equals pi, right? 0 and 2 pi are the same angle. That's why I put or here, 1, 0, 1, 2 pi. But we're going to use 2 pi because of the region that we're integrating. It makes sense if we integrate from pi to 2 pi. That's why instead of 0, we're going to use pi to 2 pi. That's all. Okay. So I'm just going to underline these two guys, this one and that one. All right, so our integral would be a equals from pi to 2 pi and then 1/2, and the inside the curve, the first curve would be 1 minus sine of theta, right? You can still see it here, squared, and then I factored out the 1/2, right? Let me bring that back. So this is that 1/2, right, in our formula, right there, 1/2 in front, and then f of theta is squared minus g of theta is squared. Okay, and then minus, the other one is minus 1 squared, right, which is 1, minus 1, if you like. Let me put the squared there as well, and then d theta. Okay, so now let us expand this and simplify what we can. So we have a equals, I'm going to put the 1/2 out in front, from pi to 2 pi of 1 minus 2 sine theta plus sine squared theta, and then minus 1, right? Minus 1 d theta. Of course, this minus 1 and this positive 1 add up to 0. So what do we get? We get a equals 1/2 integral from from pi to 2 pi of minus, or sine squared theta minus 2 sine theta d theta. And recall that useful formula that has helped us so many times. So recall that sine squared theta is equal to 1 minus cosine 2 theta over 2. And then, so let's substitute for that. We have 1/2 2 pi, and then so I'll simplify it after this, but substituting for that, we get 1 minus cosine 2 theta over 2, and then of course minus 2 sine theta d theta. Okay. One half, and then let's simplify this inside. So it's just 1/2 minus, again, 1/2 times cosine 2 theta plus, minus 2 times sine theta d theta. Okay. So now we can easily integrate this. Let's do that. I guess I can put another equation here before going to the next page. Well, let me go to, because let me do that on the next page actually. So we have area equals 1/2 times, so this will be 1/2 theta, and then this will be, this is cosine, so it must have come from sine 2 theta, and then we need to account for the chain rule. The 2 comes out, so minus 1/4 sine 2 theta. So if you have any doubts, you can take the derivative of this, and you should get that. Okay, you can quickly verify that. And then, of course, this will be positive. Yeah, positive, since we need to keep the negative positive. Positive 2 cosine of theta. Okay, I'm just double checking this to make sure that I don't have any errors. Looks good. Looks good. Okay, so pi, from pi to 2 pi. Okay, and then we don't need that sheet anymore. All right, so then let's substitute for theta with 2 pi and then pi. So we have area equals 1/2 times 1/2 times 2 pi. And I will put maybe another parentheses here. And then minus 1/4 sine 2 times 2 pi. 2 times 2 pi plus 2 times cosine of 2 pi. So we're done with 2 pi. Now let's substitute for theta with pi. So minus, and then we have 1/2 of pi minus 1/4 sine 2 pi, and then plus 2 cosine of pi. I can barely fit that there. So close the parentheses and close the bracket as well, like that. Okay, so what do we get after evaluating each term? We get, so 1/2 on the outside, 1/2 times 2 pi, that's just pi. So pi, this is sine of 4 pi, so this is just 0 times minus 1/4, so that's minus 0, plus cosine of 2 pi is 1, 2 times 1 is just 2, so plus 2, and then minus, this is just pi over 2, sine of 2 pi again is 0 times that, we get 0, cosine of pi in this corner, far corner here, minus 1. Minus 1 times 2 is minus 2. Right? So that's minus 2. Okay, so now we have some things to simplify here. We got to distribute this minus into this. So we have A equals 1/2 times pi plus 2, and then minus pi over 2, and then minus 2 is positive 2. So we have, okay, let's see. We got 2 and 2 are 4. Pi minus pi over 2 is just pi over 2. So we have 1/2 times 4 plus pi over 2. And so multiplying that through, we get A equals, so 2, right, plus pi over 4, like that. All right. Again, without graphing these using technology, this would either be taking a very long time, or we would get some erroneous results. So please make sure that you are familiar with the graphing technology. Okay. Let's do another example here. trying to keep track of time as well. So, well, we have plenty of time. That's good. Okay. Because this equipment will shut down after 4 hours, I just wanted to make sure that we are within that time. Okay. So here, this is again, I use technology to trace both curves. And this is what I came up with. And this, the circle is just r equals 3 sine theta. And the other curve, which is not a circle, has a different shape. You can see there. It's this one, 2 plus sine theta. Okay. And then with technology, you can establish what that point is, but also we can solve for it. So that's not a big deal. But sketch both of these curves on Desmos.com to come up with this on your own as well. So please don't take my graph as it is. Just verify it on your own. Okay. So the first thing we do here, the solution, technology to graph both curves. That's the first thing I recommend that you do. Okay. The next, what do you think we should do next? Let us figure out next, where do these curves intersect, right? So figure out where each other. So to do that, all we have to do is set these two curves equal to each other. So let's do that. 2 plus sine theta equals 3 sine theta, and then 3 sine theta minus, I'm just solving this equation, that's all. Minus theta minus 2 equals 0, and then this minus that, we get 2 sine theta, and 2 sine theta minus 2 equals 0, and then therefore we have sine theta equals 1. So where is it that sine of theta equals 1? That means theta has to be equal pi over 2. And what do we get for r from any equation? It makes no difference which one we use. But what do we get for r when theta equals pi over 2? So when theta equals pi over 2, r equals 2 plus, so I'm using this equation, but you would get the same result if you use this one. So r plus 2 sine of pi over 2, and of course we get, this is 1 plus 2 is 3. So the point of intersection is 3 comma pi over 2. Okay, so that's that point. Let me mark that here. That point. 3 comma pi over 2. Okay. If you do this on the computer, the lines I've drawn show that there's a space there, but if you use technology, there's no space there. I mean, it's not discernible with the naked eyes. Maybe you have to zoom in to see that there's a space there, but they are almost virtually one line when it gets to this point of intersection. Okay, so that's that. Now, so we've done that. To find the shaded region, right? So to find the, let's see, because, so we don't really need to integrate for the circle, right? We do have to integrate for the curve that is outside because it has such an irregular shape. So if we integrate for that, we get the area of that shape including the circle. So all we have to do then is subtract the area of a circle that we know whose radius is how much. The radius from here to here is 3, right? We just solved for it. From here to here is 3 units. So the radius must be 3/2, right? So we can just calculate the area of the circle using the usual area formula it has, pi r squared. Okay, so we can say for the area of the circle, pi times 3/2 squared. Pi r squared, that's all. That's all we have to do. We have no use for integration for that. But we do have to integrate from actually 0 to 2 pi, because we want to know, we want to trace we want the whole area of this irregular shape, which is generated by this curve. We want this whole area, and then we subtract the area of the circle from it, and we get the area of the shaded region. So we will have to integrate from 0 to 2 pi. But this coordinate that we found is helping us to figure out the radius of the circle. If we know it's 3 units from here to here, then the radius must be 3/2. But we're not going to integrate that. We just know what it is, right? Okay, so let me write that here because I want you guys to have this as part of your note. I'm guessing some people may not even watch the video and they might go straight to the lecture notes. So they should have that on the lecture notes for those people who decide not to watch these videos. So to find the shaded region, or the shaded area, total area of the curve, this curve, R equals 2 plus sine theta over, of course, its entire region, so which is from 0, theta varying from 0 to 2 pi. Okay. And then we'll have to subtract the area of that circle. Okay, so that is of the circle, R equals 3 sine theta from it. So, okay, that's what we'll have to do. And then let me, continuing here, so is simply pi times 3/2, which is radius, right? Radius squared. Okay, like that. Okay, since the circle is simply because, let me just add that also. That curve is a circle of radius 3/2. Okay. All right. So now we can begin just integrating this curve over 0 to 2, from 0 to 2 pi. And then we're going to subtract that area from it, which is 9/4 times pi, right? 9 pi over 4. We're going to subtract that. One half that curve only, 2 plus sine of theta squared d theta minus the area of the circle, that one, which is 9 pi over 4. Okay. All right, so then, and let's expand this. So we have 1/2 from 0 to 2 pi. And this is 4 plus 4 sine theta plus sine squared theta d theta minus 9 pi over 4. And then recall that sine squared theta is of course equal to 1 minus cosine 2 theta over 2. So then we will, let me go to my next page here. Right. So then we have the area equals 1/2 from 0 to 2 pi, right? We put the 1/2 outside, and then we have 4 plus 4 sine theta plus 1 minus cosine of 2 theta divided by 2 d theta. And of course, let me not forget minus 9 pi over 4. Okay. Okay, so we'll continue with this. So we have 1/2 integral from 0 to 2 pi. And let's break this up again like the examples we've done so far. 4 plus 4 sine theta plus 1/2 and plus, minus that minus, right? Minus 1/2 cosine 2 theta. And then we have d theta minus 9 pi over 4. Okay, taking this simplification one step further, 4 plus 1/2, that's just 9 over 2. So area equals 1/2 integral from 0 to 2 pi of 9 over 2 plus 4 sine theta. and then minus 1/2 cosine 2 theta d theta minus 9 pi over 4. Okay. All right, so now we can integrate. Sorry, my writing is going up that way. It shouldn't. So let me try to write better here. 1/2 times 9/2 theta and minus 4 cosine theta. And then, so this must have been sine 2 theta, and then minus 1 over 4. Sine 2 theta would be the antiderivative of that, and that goes from 0 to 2 pi minus 9 pi over 4. Okay. Okay. All right, so we have the area equals 1/2 of, and let me substitute for theta with 2 pi. I got to be careful because we have a cosine here. Cosine of 0 is non-zero. It's equal to 1 times -4. We're going to get -4. So I got to be careful there. But let me start with substituting for theta with 2 pi first. So we have 9 over 2 times 2 pi minus 4 times cosine of 2 pi minus 1 over 4 times sine of 2 times 2 pi, right? 2 times 2 pi. And then minus, let me, so minus, and then I'm going to put bigger parentheses here and then opening up another one. So because I'm running out of room here, let me, well, maybe I can fit it. So I'll try to, well, I will run out of room because of that. So let me substitute for theta with 0 and simplify at the same time. 0 times, so substitute for theta with 0, 0 times 9/2, 0. Minus cosine of 0 is 1. 1 times minus 4, minus 4, minus 1 over 4 times sine 0. This is going to drop out and become 0. So we have a minus 0. Okay, so that's that. And then, of course, minus 9 pi over 4. Okay. All right, so now we can simplify this further. We have 1/2 here times 2 and 2 cancel out. We get 9 pi. Cosine of 2 pi is just 1. 1 times -4, so minus 4. And then minus, this is 4 pi. Sine of 4 pi is 0 times minus 1 over 4 is 0, so minus 0. And then everything here is 0 except that. Minus 4, we get positive 4. And then, of course, lastly, minus 9 pi over 4. Okay, so 4 and minus 4 cancel each other out. We end up with area would be 9 pi over 2. And these two cancel each other out. So 9 pi over 2, oops, I forgot the 1/2 there. So 1 over 2 times that minus 9 pi over 4, right? I'm writing every step down. You were done 10 minutes ago, much sooner than that, but I'd rather write down every step just in case people have any questions about every stage of this. So then we have 9 pi over 4, or 9 pi over, no, sorry, 9 pi, this is 9 pi over 2, so I already, so no need for that. Sorry about this. I will, before I post these notes on Canvas, I will clean this up. But this is just, I've already distributed this into that. You get 9 pi over 2. So then we get 9 pi over 2 minus 9 pi over 4. So we get 18 pi minus 9 pi. And then we have, of course, area is 9 pi over 4. Again, I apologize for that. Okay. Let us look at another example of this type. So we have this curve, these two curves, and I use technology to plot these, and you can see what I ended up with here. And we want to find the area of the region that lies inside both curves. Okay. So that's the shaded area. Okay, so let us find the... So we've done the first step, which is use technology to graph this. We've shaded the area that we need to, that lies inside both curves. And so the next step is figure out where they intersect, right? We know that they're intersecting here and here, but let's find the coordinates of that. So, but I will write each step here. First, using technology, and then next, let us find where the curves intersect. Okay. All right, so that means we set these two equal to each other. So we have 1 plus cosine of theta equals 1 minus cosine of theta. So we do the algebra on this, we end up with 2 cosine of theta equals 0, and then that means cosine of theta is equal to 0. And where is cosine of theta equals 0? So theta at theta equals pi over 2 and also 3 pi over 2. Okay. This is all from trigonometry. So if you've taken the trigonometry recently, then you'll remember these pretty easily. Okay. So now we're going to need to find out what is the R value for each of these. Okay, let's find that out. So let me move this up a little bit. So for R equals 1 plus cosine of pi over 2, we have 1. So these two are equal actually. 1 plus cosine pi over 2, 1 minus cosine pi over 2, because it's 0. Whether you add 0 or subtract 0 from something, it makes no difference. So 1 minus, so that is equal to 1 minus cosine of pi over 2, which is equal to 1. So that means the point of intersection is 1 comma pi over 2. That's one of them. So that would be this one. Let me mark it out. So, oops, sorry. So that point is 1 comma pi over 2. And you probably guessed what the other one is, right? It's going to be 1 again, but this time comma 3 pi over 2. But let's find it. Let's just calculate it. R equals 1 plus cosine of 3 pi over 2 is equal to 1 minus cosine of 3 pi over 2. Again, because it makes no difference if we add or subtract 0 to some another value. So we have 1 comma 3 pi over 2. Okay. And so that one will be this point right here. Oops, my ink is drying here. 1 comma 3 pi over 2. Okay. All right, so now notice from the graph that the graph is symmetrical, right? So if we integrate, let's say 1 minus cosine theta, this one, from 0 to pi over 2, then we can multiply it because the other piece, so that piece, so from here to here, it's part of, for this curve, for the one drawn in red, would give us, from 0 to pi over 2, would give us that piece. That is a little bit, I've shaded it a little bit darker than the other three regions, 1, 2, 3, 4. So if we have that, by symmetry, these are all equal, so we can just multiply that area by 4, that integral by 4, and get the area for all of this, the shaded region. Okay, but we can take this curve, the red one, integrate it from 0 to pi over 2, and multiply it by 4 because we have 1, 2, 3, 4 such pieces. Okay, let's do that. And I will write down a comment about that. So we can integrate r equals 1 minus cosine of theta, and over the interval 0 to pi over 2. And then multiply that result by 4. Has 4 such pieces. Okay, so let's do that. Okay, so we have a equals 4 times integral from 0 to pi over 2, 1/2 r squared d theta. Only we can do this because of the symmetry involved. Okay. And then And then so we have A area equals 4 times 1/2 times 1 minus cosine of theta squared d theta. And you can see the red curve here going from 0 to pi over 2 like that. Okay. All right. So what do we get after this? We will get, so we have a 1/2 here and a 4 here. Multiply them, we get a 2. So let's do that. We have 2 times integral from 0 to pi over 2. And let's expand that. So we get 1 minus 2 times cosine of theta and plus cosine squared theta. Squared theta d theta. Okay, let me go to the next page. So here you recall that very popular formula that cosine squared theta is equal to 1 plus cosine 2 theta over 2. So we're going to, these two are easy to integrate. It's this one that we have to manipulate a little bit. And then so we have like that area equals 2 times 0 to pi over 2, and then we have 1 minus 2 cosine theta plus 1 plus cosine of 2 theta over 2 d theta. Okay, and you know what we're going to do next, right? We're going to break this up into 2 terms, one constant, one involving the cosine function. All right, so let's do that. So we have the area equals 2 times 0 to pi over 2, and then 1 minus 2 cosine of theta plus 1/2. This 1/2 and this one, of course, will combine in a second. 1/2 cosine 2 theta d theta, and then let's see. Yes, so we have the area equals that 1 and 1/2, 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta d theta. Okay, yeah, I'm just double checking this to make sure, yeah, everything is okay. Now we can integrate, of course. So 2 times 3/2 theta minus 2 times sine theta, and so plus 1 over 4 times sine 2 theta from 0 to pi over 2. Okay, so we already know for 0, theta equals 0, all these terms drop out, so we worry about just the pi over 2. 2 times, so 3/2 times pi over 2 minus 2 times sine of pi over 2 plus 1 over 4 sine of 2 times pi over 2, and of course then minus, so all of this and then minus 0 after that. 0 and that. Okay, so we have, what do we have? We have the 2 here, we have 3 pi over 4. Sine of pi over 2 is 1 times minus 2 is just minus 2. 2 pi over 2, the 2's cancel out. We get sine of pi. Sine of pi is, of course, 0. So 0 and minus 0, so we have 0 after that. So then we have, let's combine these. What do we get? We get, well, let's distribute this 2. So we get 2 times that, 6 pi over 4, which reduces to 3 pi over 2. 2 times minus 2, we get minus 4. And let's leave it like that. Of course, if you write this as 1 with common denominator, it's okay. But this should be fine. Like that. Okay. All right. So I did use technology to graph this, but it seems that I forgot to draw it on this figure. It's okay. Let's do it now. But I prefer to do this ahead of time because if my figure is not right, I'll have time to fix it. But so pardon me if the figure doesn't turn out to be that perfect, but go to this desmos.com/calculator and graph these for an accurate version of this graph that I'm going to draw. Okay, but so for this circle, this is a circle at the origin with radius 1. Like that. And then in this one is a lemniscate. It's like an infinity symbol. The symbol for infinity, it's just a lemniscate, as it's called. So let me try to also draw that. So it should go like that, and then also it would go like this, like that, something like that. Okay, and then we can draw these with different colors. And just to give it a little more contrast. Like this. And also like this. Like that. Okay, so this is again, they're asking us to find the area of the region enclosed by both curves. So then we have to shade just this piece here and this piece here. This is, when you look at this carefully, this is a little bit complicated, but in a subtle way, because you have these intersection points, right? We can see them on the graph here and there. So these are the points of intersection. We have here, then here, then of course here and here, right? But if you look at it carefully from this point, because this curve right here is not a straight line. So if you connect this point to the pole with a straight line, that small region has a different integral than the region from that point forward to the middle of this and up, even up to this region, and from this intersection point to this pole, it has a different integral. I mean, we're switching curves. This tiny region from the pole to this point, and I'm not going to draw it because, well, maybe let me draw a dashed one. If I draw a dashed line through that point, it's very subtle. I mean, it's really difficult to show it on paper, but I'm sure computers can do it nicely and very precisely. See, if we draw a line through that intersection, and let me do that another one here for the other, I'll do it just for these two. I'm afraid to continue it, but if my graph was perfectly symmetrical like a computer graph, when you draw that one and you extend it, it'll go through this intersection point. Okay? I'm not sure if I as a matter of fact, it probably won't. I mean, it's off. I know it's off, but if I draw it, barely you can see that it goes through that. And then we can do the same thing with these two guys. And but yeah, my graph is not symmetrical, so, or it's not precise, and so the line probably, let me do it this way. It's very difficult to show that, but I'll try to do as best as I can. And if I continue that here, going through the other intersection point, see the curve from this red curve, between the red curve and the dashed line, a different curve is involved than from that point forward. And then at this point, the circle stops and this other curve starts. And the same thing happening on this side. So this is a little bit complicated than the other graphs. And this one, so let me actually label this graph. We have the red one is r squared, of course, the other one, right? So we have r squared equals 2 sine 2 theta. And the circle, of course, is r equals 1. And then, so we have, so let me actually begin to write out the steps here. So I need to document what's going on here. So first thing, draw both curves with technology. Technology, right? Now, let us find the intersection points. So this one, and this one, and this one. So let us find, let's see. Let's find where the curves intersect. So where, I mean, your technology, I'm sure some of the technologies will give you these the coordinates of these points too, in which case you just write them down and you're done. But that happens when we have this curve equals that one, right? And this is r squared, that's r. So if we take the square root of both sides here, so that this is equivalent to that. So we have plus or minus square root of 2 sine 2 theta. Of course, that's just 1, right? And then again, we'll have to square both sides, plus and minus squared, to solve for theta, right? So squared equals 1 squared. And so what do we have? Let me scroll up, and then when I need the graph, I'll scroll back down again. Like that. And then so we have, this will be just 2 sine 2 theta equals 1. And then we have, so from here we get sine of 2 theta equals 1/2. So sine of what angle is equal to 1/2? It's pi over 6. So then, again, this is from trigonometry, right? We know that. So 2 pi must be equal to pi over 6. So this means pi, or theta, 2 theta is supposed to be pi over 6, and then theta. So divide both sides by 2 to solve for theta would have to be equal to pi over 12. Okay. So if I scroll down from the pole, the angle between the pole and this line, it's going to be pi over 12. So this is, I'll write it down here. So this is theta equals pi over 12. So what do you think is this one then? This is, even though my graph doesn't do justice to it, but this is pi over 2 minus pi over 12, right? Because we're taking the angle thetas from the positive x-axis to that line. So then to get the angle to this line that goes through the intersection point, all we have to do, because of the symmetry, just say pi over 2 minus this angle, we've already figured out pi over 12. And it's going to give us that angle from the positive x-axis to that line, to that dashed line. So then let's do that. So looking at the graph, the other intersection, let me just say in the first quadrant, right? Because we have intersection on the other side too. In the first quadrant is at just pi over 2 minus pi over 12. So what is this? So we have 6 pi minus pi, or 5 pi over 12. Okay? Like that. So let us then, okay, so what I'm trying to show here is that we have a region. It's easier if we go, because this graph is so symmetric. So if we go from, to simplify things, the pi over 4 line, or theta pi over 4, perfectly dissects this quadrant. So it's pi over 4, again, because of the symmetries, right through the middle of all of this. So if we do the integration, so let's see. So from 0 to pi over 12, right, it's going to give us this piece. But we have how many of such pieces? We have 4. We have this one. We have that one, even though my graph doesn't do justice to it. We have that piece. So 1, 2, 3, 4. So we have 4 such pieces from integral from 0 to pi over theta equals 0 to theta equals pi over 12. Now, this region in the middle, because theta equals pi over 4 just goes right through the middle of it, and theta, if we take theta equals pi over 4, it simplifies things. Then we can take an integral going from pi over 12 to pi over 4, which is right the middle. And then how many such regions do we have? Again 4, right? We have pi over 12 to, from theta equals pi over 12 to theta equals pi over 4. That's going to give us this piece. Again, this is to simplify things. And then we have just like that over here. I'm not drawing the theta equals pi over 4 because it's going to make this drawing way too crowded. I'm just talking about it. Imagine the theta equals pi over 4 perfectly dissects this plane, the first quadrant. So it's going to go right through the middle because of the symmetry. So if we take the other integral from pi over 12 to pi over 4 and multiply that by 4, we get the regions that are part of that are as a result of the integral of the curve that generates the circle. And then we also get the regions that are the result of the area under the curve that generates the lemniscate, this one. Okay? So we have 1, 2, 3, 4 such pieces from 0 to pi over 12. And then we have from pi over 12 to pi over 4. Let me just for the sake of clarity, let me put it just a dot there, and I'm going to say pi over 4. I hope that doesn't complicate things. And then I'm going to put a rough, because this is the most important part of the solution, so everybody can see why we're doing what we're doing. So then let me draw that right through the pole. So then we have, notice for this piece, that piece is the area under the curve that generates the circle. So we have how many pieces like that? 1, 2, and we have 2 on this side, so we have 4. And the area under the lemniscate curve, we have also 1, 2, 3, 4. So we can integrate this curve, the lemniscate, from 0 to pi over 12 and multiply it by 4 to get these pieces. And then we can integrate the curve that generates the circle from pi over 12 to pi over 4 and multiply it by 4. Okay, let's do that. I hope I was able to clarify that before we actually do that. So let me okay, so I'm just going to so how do I want to do? I want to oh, by the way, so this one I didn't write it yet, but even though we calculated it here, 5 pi over 12, that's this one. Pi over 12, right there. Okay. So let me write that in notes also, in addition to what I said. So, our integral for the shaded region has two pieces. These are the, so one piece one integral calculates the area under the circle, and the other piece under the lemniscate. I don't even know if my spelling is correct. I apologize for that if it's not. But this piece, I can't fit the, but well, I'll write it here. Under this area under the circle, that would be 4 times, and the other piece under the lemniscate. So this piece will be, and I'm talking about all 4 regions, this, and we have 2 such pieces on this side, right? So we have 4 such pieces, and we should integrate from pi over 12 to pi over 4. Pi over 12 to pi over 4. Let's see. Okay, d theta. And I'm just going from, I'm generalizing before I actually go to the integral, so you know what's going on here. Then under the lemniscate, we have 1 piece, 2 piece, 3 piece, 4 piece again. So again, we have 4 times the integral from 0 to pi over 12. In other words, we have the same exact piece happening in these different corners of the enclosed or the shaded region. Okay, so that will be 0 to pi over 12 d theta. But you got to be careful. You're only integrating the curve that generates the circle for this integral. And for this integral, you're only integrating the region that generates the lemniscate. Okay? That's the idea. Okay, so let's do that. Now that we've explained this, so let's actually put the integral together. And I hope it'll make sense when you see it. So area is equal to 4 times, I'm going to start with the lemniscate, integral from 0 to pi over 12, okay, 1/2 the radius of the lemniscate squared d theta, and then so this is that, and this is plus. So let me write this with red, so this is the important part, and then add it to this one, plus 4 times integral for the circle. It's going to be pi over 12, from pi over 12 to pi over 4, 1/2 the radius of the circle, or sorry, not the radius bar, but the polar equation, r for circle, squared d theta. Okay? I hope that is making sense now. Okay, so let me go to the next page, because I think this page is crowded enough or cluttered enough. Like that. Okay, so now we're going to put in the polar equations for each appropriate curve. So we have the area equals 4 times the integral from 0 to pi over 12, 1/2 times 2 sine 2 theta. Let's see, and we don't need to square this, right? This is r squared, and this is already r squared. R squared equals 2 sine 2 theta, so we already have r squared curve given to us for the lemniscate. All right, so like that. So no squared, this is already r squared, d theta, and then plus the other piece, which involves the circle. So I forgot to put the 4 in front. Well, maybe, I don't want to. So let me put it here. 4 times, right? This 4 should have been in front. So anyway, I forgot to put it. So 4 times 1/2, this 1/2, right? And then the polar equation for the circle was r equals 1. So all we have to do is 1 squared d theta. And of course, the limits of the integration for this piece are pi over 12 to pi over 4. Okay, like that. I don't think we need that sheet anymore, so we can continue from here on. Okay, so now we can integrate immediately, keeping in mind that we have things simplify here. Well, let me keep the 4s intact for now. So this is 4 times, and then we have minus, let's see. So this was just, these two simplify, right? So this and this simplify, but I'm going to keep the 4 here, but these two simplify, so we're integrating sine 2 theta. And that would be 1/2 or minus 1/2, minus 1/2 cosine 2 theta, going from 0 to pi over 12, and then plus 4, right? For this time 1/2. So this is just 4 times 1/2 theta. So I'll just keep the 4s. 4 times, and this is 1/2 theta, right? 1/2 theta, going from pi over 12 to pi over 4. Okay, I'm just double checking here. Okay, this should be good. Then we have the area equals, so what do we get? We get, this is just going to be minus 2, right? And that's just going to be 2. Let's distribute the 4s now. We get minus 2 cosine of 2 theta from 0 to pi over 12, plus 4 times 1/2, 2 theta from pi over 12 to pi over 4. Okay, and then let's plug in for all of this. So we have minus 2 cosine of 2 times pi over 12 minus 2 times cosine of 2 times 0, and that's that, and then minus or plus, well, let me close this, and then plus we have 2 times pi over 4 minus 2 times pi over 12. Like that. Okay. So area then is equal to, so we have minus 2, this is pi over 6, minus 2 times cosine of pi over 6, which of course is square root of 3 over 2, but we'll get to it later. And then minus, this is cosine of 0 is 1, times minus 2 is minus 2, times another minus, that's pi plus 2. Pi over 4 times 2 is just pi, reduces to, or simplifies to pi over 2. Minus 2 times that, it's going to be minus pi over 6. Okay, so these two just reduce to pi over 3. Right? So then we have the area equals, now let's minus 2 times square root of 3 over 2, and then plus 2 plus this, pi over 3. So what do we get? We get exact, the area is 2 and 2 cancel out here. So all we get is, let me put this minus in the middle, the term with the minus in the middle, so I'll just put the 2 and then minus square root of 3 plus pi over 3. And we can just leave it as that in perfectly exact form. Okay, like that. Okay, I hope this was useful exercise in finding the area between two polar curves. I thought this was an interesting problem too, so I included it anyway. And so this is just one problem on finding the points of intersection. Your book has a few problems on this. I thought, why not? Let's do one on this. Since we had to calculate the points of intersection for those other curves anyway. So here we have two curves as shown. Again, I use technology to get what you see on the paper. And we want to find all the intersection points. Where are the intersection points? We have that one, right? Let's label these. We have that one. We have, of course, notice that both curves intersect each other at pole, right? So that's definitely there too. But we already know the coordinates of that pole. It's 0, comma, theta, right? We need to find these other points so that we don't know. So that's another point where they intersect. And I didn't draw this nicely. So there is no, these two here on this side in the fourth quadrant, they intersect at the pole. There is no fourth, see, there is an intersection point here. But that one is, if we draw it better, let me see if I can just like that. And then like that. Right here, this point of intersection, there is no point of intersection along the way in the fourth quadrant. There is none. It's because my drawing is not accurate. So these two intersect at the pole, right, like the other leaves of these two curves. So these are the only points of intersection besides the pole. So let's label these. This is A. Let's call this A, point B, and point C. Okay. Okay, so then points of intersection occur when these two are equal, right? when cosine of 3 theta equals sine of 3 theta. So we can solve this equation for theta. We can do sine of 3 theta divided by cosine of 3 theta. We could do cotangent, but tangent is always better to work with than cotangent. It's more common, and so equals 1. And then so this way we get tangent of 3 theta equals 1, right? So that means the tangent of pi over 4 is equal to 1. So then 3 theta should be equal to pi over 4. And of course, for any other equivalence, so plus n pi, where n equals any integer, right? So then if 3 theta is equal to that, then theta, it's going to be equal both sides divided by 3, and we get theta equals pi over 12 plus n pi over 3, like that. Okay. So let me just add, because we don't want to forget about that, that the pole is also a point of intersection. I'm just going to make a note of it here. That the pole 0 comma theta so we know that already. So I'm going to box it. So that's one of the intersection points. So the other intersection points A, B, C points A and B and C are as follows. We simply start by incrementing this n, which can be any integer, for 0, 1, and 2. So let's do that, those 3. So when n equals 0, then we have theta. What happens when we, oh, it's on the screen, good. So right there, let me actually highlight it here. And so that. So when n equals 0, theta equals pi over 12. Pi over 12, and then we can calculate r, right? Because for the polar coordinates of these, we need r and theta. So for A, we got n equals 0, theta equals pi over 12. So we need to find r as the other coordinate of this polar coordinate for this point. So let's find r. Which would be cosine of 3 theta, or 3 times pi over 12. So this is cosine of pi over 4. We know that is equal to square root of 2 over 2. therefore point A has these coordinates. It's got r is that, so square root of 2 over 2 comma the angle, which is pi over 12. Okay, and then I will box it like this. So this is point A. Okay, so when n equals 1, then theta is, what is theta equal? If n equals 1, we get pi over 3 plus pi over 12. Common denominator would be 12 pi plus 4 pi. So we get 5 pi over 12. Right? So 5, well, let's see. 4 pi. And so let's see what we get. 1 pi over 3, and that's 4 pi, and plus 5, so 5 pi, 5 pi over 12. So 5 pi over, I don't know why that took me so long, but that's 5 pi over 12. Okay, then let's find the r value for that theta, which would be r equals cosine of 5 pi times 3, right? Times 3, because we have 3 theta. So 5 pi, which is theta times 3. I should have put the 3 before, but it's okay, just like that. Instead of 3 times pi over 12, 3 times 5 pi over 12. And so we get cosine of 15 pi over 12, and that reduces to cosine of 5 pi over 4, right? 5 pi over 4. And then this is still, it's in the third quadrant, so it'll be cosine in the third quadrant is negative. It would be negative square root of 2 over 2. Okay, so this is the r, and we know that is associated with this angle, 5 pi over 12. So let me write that down. So we have negative square root of 2 over 2, and at this angle, 5 pi over 12. And this is our point B, coordinates of point B. Okay, so one more, coordinates of point C, right? We've got this, this, and now this. All right, so that will happen when n equals 2. Right, like that. So what happens when n equals 2? We get 2 pi over 3 here, and then plus pi over 12. So 2 pi over 3 with common denominator 12, we get 8 pi plus pi, 9 pi over, let's see. And so when we get, so we get 9 pi over 12, or theta equals, well, let's simplify it. Let me simplify it on paper. So theta equals 9 pi over 12, or 3 pi over 4. Okay? Okay, so now we will, well, since the curve is 3 theta, then I will say r equals cosine of 3 times theta, right? 3 times 3 pi over 4. Okay, so this will be cosine of 9 pi over 4. 9 pi over 4 is 8 pi over 4 plus pi over 4. So we're going to be in the, and 8 pi over 4 is 2 pi, right? So 2 pi plus pi over 4, we're going to be in the first quadrant. In the first quadrant, cosine is positive. So cosine positive square root of 2 over 2. So this will be, oops, square root of, I should clean this up before posting it on Canvas, square root of 2 over 2, or maybe that's clear. Anyway, that's square root of 2 over 2 in the first quadrant. So then this point, we have square root of 2 over 2, just like point A, comma, theta being equal to 3 pi over 4. So that's the only difference with that. So 3 pi over 4. Like that. And this is point C. Like that. All right. So we did one example for finding the intersection points only. All right, so we've talked about how to calculate the area under a curve for which we have a polar equation. Then we talked about calculating the area when we have two polar curves and we want to find the area enclosed in between them. So that was just the area in different in different forms, in different situations. Here we're going to calculate the arc length. We've done this before, right? We've done this when we had an equation with x and y involved. But we haven't done this when we have polar coordinates or polar equations involved. So this is about that. So to find the length of a polar curve, where of course the equation is given in polar form, when theta is changing from A to B, and x is equal to that and y is equal to that, then the length of the curve is obtained using this formula. R squared, so the polar equation is squared, and then the derivative of the polar equation is squared. Added to that, take the square root, integrate from A to B, which are the limits of theta, limits of integration for theta. Okay. All right, so let's start with this example. I would, if you actually do this, go to desmos.com/calculator and graph this, and then zoom out. I didn't draw the graph for this because it's probably going to make things more confusing if you have the graphs for this. But it's just, without the graph, it's much easier. Just integrate this according to this formula. Take the derivative of it. That would be dr d theta. Square it, add it to the original curve squared. Take the square root of it and integrate it from 0 to 2 pi. It's less confusing that way. But the curve keeps going around and around, and it folds on itself on different quadrants of the plane, and so it's better if you don't graph this one. This was an exception. So it's really straightforward and easy if you just integrate from 0 to 2 pi and use this formula with this polar equation. And we're going to do that. So we have, well, let me first calculate dr d theta. So dr d theta is simply the derivative of that which is 2 times e to 2 theta, right? And then the length of the curve, maybe I can still bring it on the screen. Yeah. So we're going to apply that. So length is integral from 0 to 2 pi. Let me move it up a little bit. And then square root of let's see, so r squared, which is this squared, e to 2 theta power squared, plus, right, plus dr d theta squared, and that's that, 2 times e to 2 theta squared, and then d theta. Okay, we don't need that anymore, the formula. And then, so L would be equal to 0 to 2 pi, square root of, distribute the power, what do you get? You get e to 4 theta, plus, again, 2 squared is 4, times e to 4 theta d theta, right? So then we have 0 to 2 pi, and then these two we can add, so we get 5, right? Let's do that. 0 to 2 pi square root of 5 e to the 4 theta power d theta, right? 4e to the 4 theta, and plus this, we get 5 times that. So we can factor out square root of 5, and then that piece is easy to see how that piece comes out of the square root as well. So let's do that. L would be is equal to square root of 5 times integral from 0 to 2 pi of square root of e to the 4 theta d theta, right? And then we have, let's see, so that's just e to the 2 theta, right? This is just e to the 2 theta. So I will, well, let me write it here. I'm going to write the rest of this on this page. I think that will be enough space I need. So we have L equals square root of 5, integral from 0 to 2 pi of e to the 2 theta d theta. And then we have, so we can integrate, right? So L equals square root of 5 times 1/2 that. So 1/2 e to 2 theta from 0 to 2 pi. Okay. We can just pull this out too. We can just write square root of 5 over 2 times e to the 2 theta from 0 to 2 pi, and then so that would be 1. Okay, so we will have L equals square root of 5 over 2. If theta is 2 pi, we get e to the 4 pi power. If theta is 0, we get e to the 0 power, which is 1, so minus 1. And I think that's just good enough. We can just leave the answer like that. Okay, so that's the length of that arc when we have the equation of the arc given to us in polar form. Okay. Okay, let's do another example. This one was useful for when we have the graph for this one. So I drew it. And so here, remember here we don't care about the area, we just want to calculate the length of the arc, not the area enclosed within this cardioid, which was what we did. We did one example where we had half of it. We wanted to calculate half of it. So we integrated from 0 to pi, right? If you go back over the notes or the video, you'll see that example early on in this lecture series. But here, we just want to calculate the length of this arc, not the area of it. Okay, so we're going to apply this formula that we just learned about. Okay, so we have, first thing we want to calculate is dr d theta, right? That's one of the pieces we need in our formula. So dr d theta is simply, so if you distribute this, you get 2 plus 2 cosine theta. So the derivative of 2 cosine theta would be minus 2 sine theta, right? So take the derivative after you distribute the 2. Well, let me do it because I'm afraid some people might have then. This might confuse if I just jump to this. So r equals 2 plus 2 cosine theta. Now, using that, take the derivative and you'll have that, right? We all see this now. Okay, so then applying the formula, we have the integral from 0 to 2 pi then. So 0 to 2 pi. Okay, so 0 to 2 pi, and then what do we get? We get, so square root of, right, let me see, I have a question, if I remember that formula correctly or not. Okay, there's no 1/2 in this formula. Okay, so for 1 second I thought there is a 1/2. There is not. So square root of r squared. Well, I'll just write the formula first. R squared plus dr d theta squared d theta, right? Now, so that's going from 0 to 2 pi, right? Counterclockwise. Okay. Then, so let's plug in for each piece, like that. And so we have the curve equals integral from 0 to 2 pi, square root of r squared would be simply that you can still see it, 2 plus 2 cosine of theta squared plus dr d theta, right? This is our dr d theta, and dr d theta is squared. So minus 2 sine theta squared d theta. Okay, so what do we have? We have 4. So we have this equals from 0 to 2 pi, and then we have, let's expand this. We have 4 plus 8 cosine theta plus 4 cosine squared theta. And then plus this squared, we get 4 sine squared theta, right? Plus 4 sine squared theta d theta. Okay. All right. So clearly we can factor this out. And if you remember that, well, let me write it down. So recall that cosine squared theta plus sine squared theta equals 1, right? So if we factor out 4 from these two, that's what we get. So 4 times 1 is 4. So that's where I'm headed. Okay. All right. So we have, then let's rewrite this. We have integral from 0 to 2 pi. And we have the 4, well, we still have to, so let's see. So this is, so this would be 4 times 4 and 4 would be 8. So, well, let me include it. So I don't want to skip that. So 4 plus 8 cosine theta plus 4 times, I'm factoring the 4 from these two. So cosine squared theta plus sine squared theta d theta, right? And of course, this piece is equal to 1. We already noted it. So what are we going to get? We're going to get, so this is equal to 1. And 4 times 1 is 4 plus 4, we get 8, right? So we get 0 to 2 pi square root of 8. 1 times 4 is 4 plus this 4, we get 8 plus 8 cosine of theta, right? Of course, this can be factored out nicely. So let's do that. So we have the length of the arc from 0 to 2 pi is equal to square root of 8 times 1 plus cosine of theta, and then d theta as well here, d theta. Okay, so now we have to manipulate this a little bit so we can integrate it easily. So let's see what we can do. So let me move this up. So we have we've used this one several times. Cosine 2 theta over 2. Now by extension, so we're going to extend this concept, this formula. We can manipulate the integrand, this integrand. Such that, so I will, let me factor out square root of 8 out and put it in front. So we have square root of 8 times integral from 0 to 2 pi. And now, instead of that, let's rework this. And there is a good reason for it. So I'm going to write the rest of this, which is 1 plus cosine theta. I'm going to write it as a square root of 2 times 1 over 2 times 1 plus cosine theta. Right? So instead of, because when you distribute the 2 into 1/2, you still get 1 plus cosine theta, right? Which is what we had. So we didn't really change the inside of the square root, but this change made it easier for us to use this, a version of this formula, to make it easier for us to integrate this expression. But this time, we usually go, so far in the example you've seen, we've gone from this side, we converted from this to that. Now we're going to go the opposite. Okay, but if we have 2 theta in the formula and theta here, what would theta have to have been? It would have to have been theta over 2. If theta is theta over 2, then 2's cancel out, you end up with cosine theta here. Okay, so let us then I'm gonna go to the next sheet here. So we're going to say square root of 8 from 0 to 2 pi, and then so this square root of 2, so let me do that. So I'm going to separate these. So we have a square root of 2 here, then we have square root of the rest of this, so times square root of, instead of that, cosine squared theta over 2 d theta. Okay, so now if you apply the formula, and let me just apply, you can still see it. Let me apply this formula on a piece of scratch paper, right? If we have, so we know, I'm just going to use, we know that, right? Sorry for this, but this, I'm just going to use this as a scratch paper. So we know that cosine squared theta is equal to 1 plus cosine 2 theta over 2, right? So now cosine, if instead of theta we have theta over 2, therefore cosine squared theta over 2 would be equal to 1 plus cosine of 2 times theta. Our theta is theta over 2. In this formula, our theta is theta over 2. So 2 times theta over 2 divided by 2. Now, this 2 and this 2 cancel each other out. We end up with 1 plus cosine of theta over 2. Okay? So that is what we have here. 1/2 times 1 plus cosine theta. That is what we have here. 1 plus cosine theta over 2. Okay? That's why we can make use of that. Why did we do that? Why did we go backwards this time? Because, of course, if you look back at the beginning of the video, somewhere along the way, I think within the first half hour of the video, I'm not sure though, I think it was within the first half hour, I mentioned that sometimes we go the other way because of if we have a square root and we have a cosine squared or a sine squared, then these two cancel each other out nicely. And this is one such occasion. Okay, so now I'm going to multiply this by that. What do we get? We get square root of 16. This, of course, will be 4 eventually, right? 0 to 2 pi. And then this, we can remove the absolute value, but the rule is remove the radical expression, but of course we have to include the absolute value. So cosine, absolute value of cosine of theta over 2 d theta. Let me put the absolute value bar there. Now, to integrate this, of course, we need to remove the absolute value, right? So let me bring back the graph. So if we remove the absolute value and integrate over the positive values of this curve, right? The R value, R representing the polar equation of this. So R would be positive anywhere from 0 to pi. So because of the symmetry, if we remove the absolute value, we have to look at the positive and the negative one to get the full curve, right? But the other thing we can do, because this curve is so symmetrical, we can remove the absolute value, consider the positive values of this curve from 0 to pi, and multiply that integral by 2 to get the other piece, to get this piece, which it has negative r values. So we can do that. So we can change these limits of integration from 0 to pi, but by symmetry we can multiply the whole thing by 2. The nice thing about that, if we integrate from 0 to pi, we don't have to worry about the negative p, this inside being negative. Okay, so let's do that. And I will write, well, let me actually simplify this. So L equals square root of 16 is 4 times 0 to 2 pi absolute value of cosine of theta over 2 d theta. Okay, and the absolute and the square root and this power canceled each other out, this 2 and the radical expression. So now to remove the absolute value before integrating, right? Let me write that as a note. The integral from 0 to 2 pi oh, well, let me let me 0 to pi. I will clean this up before posting the lecture notes. But theta from 0 to pi only has positive values of cosine of theta over 2, right? Because that will be just pi over 2, and from 0 to pi over 2 cosine is positive. So and so by like that, positive values of this, and by symmetry, by 2. Okay, and that helps us get rid of the absolute value easily. Okay, so we're gonna change the limits of integration from 0 to 2 pi to 0 to pi, and then multiply our integral by 2. That's what we're going to do. So here it is. So we have, oops. So the length is that, we had 4, now times 2, but now notice the limits of integration. Instead of 0 to 2 pi, we'll go from 0 to pi, but we have this 2 in front, so we don't have to worry about, and then we don't have to worry about the absolute value because we have cosine of, we're only considering the positive values of this function, and then d theta. Okay, so what do we end up with? We end up with L equals 8, and we can integrate this. We can integrate immediately. So times, this will be 1 1/2 or 2 actually. So the chain rule gives us a 1/2 from this. So we need a 2 to balance that. So this is 2 sine theta over 2, integrated from 0 to pi. Let's double check. So if we take the derivative of this, what do we get? We get 2 cosine of theta over 2 times 1/2. And we get 2 times 1/2 is just 1, and we get cosine theta over 2. Good. All right, so now we can evaluate this quantity. We have L equals 8 times 2 sine of pi over 2 minus 2 sine of 0 over 2. So this piece is just 0, is 0. That one, this pi, sine of pi over 2 is 1. And so 2 times 1. So this is the length of that figure is equal to 16 units, like that. Well, I hope this session was worth your time, and so I count on the fact that if you have any questions, you'll let me know. For now, have a nice day, and I hope to see you guys in class.